Welcome back, students, to Chemistry Unit 2, the atomic model of matter. Today we'll be focusing on average atomic mass. When talking about the molar mass of a substance, we're using the decimal point numbers off the periodic table. Those decimal points are the average atomic mass of all the known isotopes of an element. So all atoms that have the same number of protons are the same element. Anything with 6 protons is automatically a carbon. Anything with 8 protons would be an oxygen. However, not all oxygens and carbons are the same. They can have different masses. So in order to figure out the mass of an individual atom or individual atoms within a sample, we use mass spectrometers. A mass spectrometer takes a sample, heats it into a gas form, and passes it through a magnetic field. The magnetic field warps the path of that gas so that lighter elements hit a detection plate differently than heavier elements. And we look at the mass of those individual atoms to determine their individual makeups. So if we have the mass of some atom of carbon-13 in grams, and we divide by the mass of carbon-12, which is the basis for our average atomic mass units, we get some ratio. We define carbon-12 as 12 atomic mass units, so if we multiply that ratio by 12, we get the individual mass of our sample of carbon-13. Now, carbon-13 is different from carbon-12 because their masses are different. The carbon-13 is an isotope of carbon. Isotopes are the same element. They all have the same number of protons, and if they're neutral, the same number of electrons. So they have the same chemical and physical properties. However, where isotopes are different is that they can have different masses based on the number of neutrons they have. So for example, the most common form of hydrogen is protium, a single proton with a single electron. However, hydrogen comes in other flavors. Hydrogen can be a little heavier by having 1 proton and 1 neutron for a mass of 2. This is known as deuterium. It is the same as hydrogen, has the same chemical and physical properties, it's just slightly heavier. And in very rare cases, a hydrogen atom can have 2 neutrons and a proton for a mass of 3 atomic mass units known as tritium. Exceedingly rare, but it is an isotope of hydrogen. Now, if you take a weighted average of all the isotopes of an element, you end up with its average atomic mass. And that is the decimal point number you see on the periodic table. It is a weighted average of all the known isotopes. On the periodic table, you will see some average atomic masses in parentheses. For example, neptunium has an average atomic mass of 237, but it's in parentheses. That is because there are no stable atoms of neptunium. It decays rapidly, and so we have a theoretical mass, but we cannot find an average based on the isotopes present. So to find the average atomic mass, it's a weighted average. Not all masses are weighted the same. They're weighted based on their percent abundance. Within a sample, what percentage of that sample is one isotope versus what percentage of that sample is a different isotope. So we will take the percent abundance of one mass and multiply by the mass of that isotope. And then we add to it the mass of the second isotope times its percent abundance. That percent abundance weights the average. So if you have something whose average atomic mass comes out to be 15.9996, like oxygen, you could probably assume that most of oxygen is oxygen-16, and then you got a couple few atoms that are lighter, maybe a few that are heavier, but most of the sample is probably oxygen-16. It's probably had the biggest percent abundance. Now that's a general rule of thumb. It's not always true. For example, Bromine's average atomic mass is 79.9, so you would say, oh, well, bromine 80 has to be the most abundant. But that's not true. In fact, there's no such thing as bromine 80. Bromine 80 is highly unstable. Only bromine 79 and bromine 81 exist. They exist almost 50% of the time, and so averaged together, they come out to be very close to 80. Now on the AP exam, you will need to be able to calculate the average atomic mass using the percent abundance. So find example 4 in your packet. Example 4 says that copper in a sample has two masses, 63 and 65. Using the percent abundance from the sample, find the average atomic mass. So our average atomic mass is going to be, if we take the mass of 63, multiply by the percent of 63, and add to it the mass of 65 and multiply by the percent of 65. And they want us to use the actual masses off the mass spectrometer. So we're not going to use 63, we're going to use 62.93 for the mass of 63. The percent abundance, we're going to use 69.09%. Now, percent, if you did not know, the word percent is actually an abbreviation, per centi, meaning for every 100. This is a mathematical operator. It simply means divided by 100 for each 100. So you won't put 69.09 here, you would put 69.09 for each 100. So we're going to take that and add to it the mass of 65, so 64.93, times the percent of 65, 30.91 for each 100. So the average atomic mass of our copper sample here comes out to be 62.93 times 69.09, 43.478 plus 20.069. So the average atomic mass from our sample comes out to be 63.55 atomic mass units, or 63.55 grams for every 1 mole. And yes, you could find that on the periodic table. The periodic table would provide a good check for an element that is known. But again, you should calculate it based off of the problem because not all samples are the same. We can use the average atomic mass off the periodic table to find the percent abundance. So argon has two different isotopes, 39 and 40. Given the average atomic mass of the periodic table for argon, what is the percent abundance of each isotope? So average atomic mass would be the mass of argon 39 times the percent of 39 plus the mass of 40 times the percent of 40. And while we know this value and we know this value, we also know this to be 39.948, given off the periodic table. The percentages we do not know. Now, mathematically, when you don't know a percentage, you assign it a variable. So let's call this x, and we'll call this y. So now you have two variable math. You've got 39x plus 40y has to equal 39.9. You can't solve two variables. You have to get one alone. You have to isolate one. But what do we know about percentages? A percentage is out of 100 for each 100, meaning x out of 100 plus y out of 100 has to equal 100, or x plus y has to be 1. meaning I could use this known definite value has to equal 100 to figure out one or the other. So I could rearrange this and say, okay, or 1 minus x has to be y. And then I could plug that in. I could substitute y for 1 minus x. Because after all, y has to equal 1 minus x. And now it's straightforward algebra. 39x plus 40 times 1 minus x has to equal 39. We can distribute. We get 40 minus 40x plus 39x has to equal 39.948. Combining like terms, we get negative x plus 40 equals 39.948. So I get a negative 0.052 equals negative x. Divide by negative 1 on both sides to get that x is 0.052. Or the percent of 39 would be 5.2% by multiplying by 100. By subtraction, the percent that's 40 would be 100 minus x. So the percent 40 would be 94.8%. With that being said, you are able to do the 5 note quiz questions for 2.3 in the back of your packet. Notice that 3 and 4 require no actual calculations. You need only know the mathematical process by which we calculate average atomic mass. Towards that end, example 3 in your packet is advanced. Thus, it came from my AP lecture series. You do not need to focus heavily on that problem. It is additional information, extra edification for your class. That being said, it is testable, thus it will be one of your free response questions. In class, we did several pages. We did page 16 in your packet, which focused on average atomic mass and simple isotopes. I also handed out practice 3.2, which focuses at first on conceptual ideas, numbers 1 through 5, and numbers 6 and 7 were mathematical. If you can do 1 through 7 on practice 3.2, then you understand average atomic mass to the depth that the state of Virginia asks you to know. However, for my class, you do need to be able to calculate average atomic mass for your free response on your test. Towards that end, next class, we will be practicing average atomic mass by doing the Beanium lab, calculating the average atomic mass of a fictitious element, Beanium. After that, we will take a quiz. On that quiz, you will have to write the isotope notation for an element. So for example, if we have aluminum 28, the isotope notation for aluminum 28 would be the elemental symbol for aluminum, Al. The mass, 28, is a superscript, and as a subscript, aluminum's atomic number 13. From that information, you will have to tell me the number of protons, neutrons, and electrons, which is what we did in example 1 in your packet. You also will then have to assign an element, a fictitious element, to a family. Remember, that is from Unit 1. At the end of Unit 1, so Unit 1.3, I believe, we went over the families on the periodic table, Group 1 being alkaline metals, Group 2 being alkaline earth metals, column 17 being the halogens, and column 18 being the noble gases. You need to be able to assign an element into one of those families. And lastly, you'll have to determine the average atomic mass, much like we did on page 16. As long as you can do all that, you will be ready for your quiz. Next class, we will do a lab. The class after that, we will take our quiz and begin 2.4 nuclear decay and nuclear reactions. See you next time.